Okay, so the last class I teach the continuity equation for the differential form. Actually, you cannot find out the material on the textbook. This is I just put on the slide. So because it's very important for this at the chapters 5. So this is the final formula. We can see the density change with the time plus the spatial gradient dot product with the velocity factors will equal 0. Okay, and as I mentioned the previous, I emphasized I wondering to explain how the physical meanings if we looking from the continuity of the differential form. So I follow these ideas. The first assumptions I use is if I assume the flow is steady flow. The steady flow indicates the density and the density cannot be changed with the time. That indicator is steady. Okay? So the first I assume the flow is steady flow. And the second I assume the condition is the incompressible flow. That indicates the density also cannot be changed with the spatial difference, which indicates all the locations of the fluid particle with the same density. So that indicates the flow cannot be compressed. So we can say that the incompressible flow. So the final formula I write down in here is the spatial gradient dot product with the velocity equals 0. Just under the condition is the steady. The first is a steady flow, and the second you can say that is the flow also incompressible flow. So if you have the velocity field v vectors, and you do the dot product with the spatial gradient, and then the final answer is 0, that indicates the flow is steady flow and the incompressible flow. So you can compare, as I mentioned before, if you do the cross product and equal 0, and you can say that the flow is a rotational flow. So different condition, we will have different meanings, the physical meanings. So you should keep in mind the two product. One is a cross, and another is a dot product. And you can calculate very quickly if you have the velocity field. Okay. So that is one cartoon figure, but not the correct, totally correct. But you can image along the y-axis, you can see the u velocity, and the u velocity here, and the u velocity here. That indicates the u velocity along the x direction is become smaller. So you can say, in that case, sorry, I can change the color pen. So you can say that the du dx is less than 0, right? Because along the x direction, the u velocity is decreased. And then if we assume the point here is a propagator outside, you propagate outside, and you see the velocity u, the v velocity initially is smaller, and become larger and larger. So that indicates we will have the dv dy larger than 0. Okay, dv dy are larger than 0. So one positive and one negative. If you both go back to see the differential, we have the divergence is equal to 0. So that indicates, based on the differential form of the continuity equation and under the steady and the incompressible flow, we can say that divergence is 0. That indicates the du dx plus the dv dy will equal to 0 if the flow is 2D flow. If the 2D flow. So you can see here, that's the reason why one negative, another is the positive. And the plus together will equal 0. That satisfies the continuity equation for the differential formula. Okay, so how powerful if we have a differential form of the continuity? That's because if you don't know the velocity field, but you know your velocity field satisfies the steady flow and the incompressible flow, and your velocity field always satisfies the equation showing here. Okay, your velocity field always satisfies the divergence of the velocity field equal 0. So how can we apply the ideas for these equations? So as the sentence I showing here, we actually know the flow is 2D flow and the incompressible and the steady flow. So we know that the velocity field satisfies the divergence is equal 0. And we can rewrite this is a du dx plus the dv dy will equal 0. Okay, so the question is, can you find out the velocity field phi? If you know the velocity function u, x, and y is 2D flow, so we have the x and the y. And then this is the minus x and y and the capital U. Okay, we only know the velocity function for the u. And we also know the boundary conditions is the v velocity x, but when the y location located at the 1, and they will always equal 0. They will always equal 0. So we only have the two conditions. Can we figure out how large the v velocity? So the first, we know that the du dx can be written by the dx, and the function here is the minus x, y, and u, right? And you can calculate the differential with the x very quickly. So the final answer is minus capital U and y, right? So we know that we have the answer, and then we can put back into the divergence. Okay, so the equation can rewrite to be the minus capital U and the y plus the dv dy equal 0, right? And then we know that the dv dy equal to u divided the y. So I can do the integrations because I keep the dv on the left hand side, and right hand side we have the u, y, and dy, and we can do the integration, right? We can do the integration both sides. And after I do the integration, because we don't have the integration interval, so we need to have maybe there are some additional functions. We call that the f, and should be the fx. Because any x function, you do the differential y is equal 0. And we may have the one constant values. We don't know how large the constant value. Okay, so after you do the integration, so you know that the v, x, y functions will equal to, you do the differential integration, so the u long y plus the fx and plus the constant values. Okay, it is almost the final formula for the velocity v. But as you remember, we have the condition boundary is at any x point, but the y located at the 1 always equal 0. So we put this boundary condition inside these equations. So you know that the v x but the y equal 1, and the first item here is 0, and plus the any x locations plus the c will equal 0. So that based on this boundary condition, we know that the fx plus c should be equal 0, right? So we can conclude that the final answer for the velocity u v x y functions will always only equal to the capital U and the long y. So the idea, how can we apply the continuity equations? Because we only know the u velocity, we don't know the v velocity. But we know the velocity field is satisfied the incompressible flow and the steady flow. So we can apply the divergence rule to based on these balance equations, and then we can figure out how large it is of the v velocity. Okay, so this is a very good exercise. We can try to practice how can we apply the continuity equations. So again, I wanted to emphasize the two importance. The first one is the divergence. So the dot product. Another is the cross product. And the different calculations have a different physical meanings. So this is we discuss with the irrotational flow. This is we discuss with the steady or incompressible flow. So different formulas, we will have different physical meanings. Okay? And the following slide, I just summarize all ideas. As I mentioned before, previous slide, I have teach you how can we determine the string functions. How can we determine the string functions? And in here, I define, we have the perceived variable in here. And I decided that the u velocity will equal to the minus d perceived and dy, and the v velocity is equal to d perceived dx. And as you remember, how can we find out the string functions? I tell you the string functions we can calculate from the velocity gradient, right? The u divided the v will equal to the spatial gradient. Okay? As I teach you before, we just follow this idea and we can find out the string line. But in here, I don't use this idea. I just tell you, I define the perceived function is a string line functions. And then the string line function will satisfy the two equations follow here. Okay? And then I wanted to teach you if your flow is irrotational flow, so you should satisfy the cross product equal 0, right? So if we put the two equations into this formula, and finally we can derive the equation, we call that the Laplace equation. Laplace equation is, we call that is the second differential, right? Will equal 0. Okay? So that's the idea. If your flow is irrotational flow and the perceived function is a string function, the string function will satisfy the Laplace equations. Okay, if your flow is irrotational flow. So just the idea I would like to emphasize here. And the second I didn't teach before is the potential function. Okay. And sometimes we call that the 四流函数. So I use the phi in here. It's a potential function. The potential function is very easy to understand because if we define a string function like this, and the potential function just perpendicular to the string function. So the potential function and the string function, they are orthogonal chained, okay? And I define with the different definition here. I define dx is u, and I define dy is v. And if your flow is incompressible flow, so you satisfy the divergent rule. And finally, incompressible flow and the potential function also satisfy the Laplace equation. Okay. The most of the material I'm showing on the slide, you cannot find out from the textbook. So this is just the idea I wondering to share with you and put on the slide. So you just keep in mind some different calculation. We will have different physical meanings, and we can apply the different physical meaning to figure out the velocity field. Okay, so this is our final exercise for the Coulter flow. And how can we determine the string function? How can we determine the string function of the Coulter flow? And as I mentioned before, the Coulter flow actually is a rotational flow. So because it is a rotational flow, so it does not satisfy the Laplace equation for the string functions. Okay? But we know that the string function, the definition is we have the u, and we know that minus the per c d y is equal to the u velocity. And v is the d per c dx, right? And the per c here is our string function. We directly call that the string function. Okay? So, as I mentioned, the Coulter flow only have the u velocity along the x directions. We only have the u velocity. And there is no velocity along the y directions. So we know that the first idea is the v equal to per c dx will equal 0. So you will know that the per c function x and y should be the function of the y, right? Because any y function is differential with the x is equal 0, and multiply the constant value. I didn't know how large the constant values. And the second condition here, we actually know the the Coulter flow, we know that the linear velocity gradients. So the u is defined here. So we have the u is the capital U, and the length, the depth in here, and the y functions will equal to the minus d per c dy, right? So we can rewrite the equation d per c and the minus u L, and we have the y and the dy, okay? So we can do the both sides, do the integration. We can do the integration, okay? And because we don't know the interval of the integration along the y, so after we do the integration, we have the additional g function, but it's an x function. Because any x function differential with the y is equal 0, and we don't have the constant value c2. So after I do the integration, I know that the per c function xy will equal to the minus 2L u and the y squared, and plus the gx and plus the c2. So you can compare the two equations, the a and the b. So you have the a and b. So you know that the per c function yx, okay, and you have the y function here, and there is the y function. So you know that the Fy should be equal to the minus U2L Uy squared. And you don't have the X function, so the Gx is 0. Okay, and we cannot figure out how large is the C1, C2. So finally, you may say that your string function will equal to a minus U2L and the Y squared. And you can define the different constant values, and then you can draw a different curve line of the string function. Okay, so the idea is if you know that the velocity, the idea we define here, and you have the u or you have the v function, and we can plot the string line. Okay, so the previous slide we don't know the velocity field certainly, and we can base on some continuity equation of the differential form to figure out the velocity field. After you compute the velocity field, you can, based on the equation showing here, you can draw the string line. Just if you know the u velocity and the v velocity, and you can define the string line functions. Okay, so this is C is the constant values. Any constant value you can put in here. If C is 0, and you can draw a line. If C is equal 1, and you can draw another line. So all the string lines should be parallel to each other. Okay, so that today we almost finished the chapter 5, and some material you cannot find out from the textbook. So if you're wondering to read some details, you can follow the slide I show in here. Okay, 好。